All right. Good morning, good afternoon to everybody joining us today, wherever you're sitting across the world. Thank you for taking the time out of your day to join us. We're very excited to be here today to present this Mike Academy presentation. Today we'll be recording this session. This means that we'll be holding all questions until the end of the presentation so that we have one continuous recording. We will also disseminate this recording to everybody who is on the call today, as well as a PDF copy of the slides. So please do hold your questions until the end of the session. And in the meantime, if you have questions that come up, you can enter those into the chat as well. And we will try to answer those at the end. So again, thank you for joining us today. This is a Academy presentation by DHI featuring our Mike by DHI products. And the topic of today's presentation is investigating coastal resilience, assessing compound flood risk and climate adaptation with Mike powered by DHI tools. Our presentation will be approximately 45 minutes, followed by 15 minutes of questions. So the objective of the presentation today is to leave you with an impression of how the Mike powered by DHI integrated software can be used to assess compound flooding along urban coastal waterfronts within the context of a changing climate. So we'll be going through various DHI software products that were used in a case study specifically. And the case study will go through the steps of developing the model and then using it to investigate compound flood risks, and then taking it a step further to investigate how solutions can be developed to mitigate some of this flood issues. So the speakers today is first myself. I'm the project director and the senior coastal engineer for DHI, the Marine and Coastal region in the Americas Pacific. I'm joined by my colleague, Dr. Renan Ribeiro, who is one of the senior modelers here that's worked on this particular case study in Buffalo. And he is sitting in Brazil. And also joined by my colleague, Derek Eden, a coastal engineer sitting in the Greater Toronto area, who is going to tell you a little bit about the visualization techniques that were used to demonstrate the compound flood effects in the case study. So the agenda for today is just a very quick introduction to coastal compound flooding in a changing climate. I'm sure most of you on the call are very familiar with this topic, but we do want to set the scene a little bit as to the kinds of mechanisms that are driving the flooding that we'll be addressing today. Then we'll quickly touch on how the Mike by DHI numerical modeling suite can be used to assess compound flooding. And that'll all then wrap up in a very detailed case study where we worked in the city of Buffalo to assess compound flood risk along the lake shore of the city. We'll go through the steps of developing the model, gathering all the information and model input data, setting up the model themselves, and it is essentially a downscaling of a regional model to a local model, and then a very high resolution lot level based model with different flood mechanisms. We will also talk a little bit about the integration of the model with other Mike tools, looking at sewage backup, for example, that's driven by storm surge, and also looking at complex flooding due to waves, with ponding and pooling of waves in areas with a lot of wave overtopping. Finally, we're going to wrap up today talking about the various methods that are available to communicate model results, everything from traditional outputs in the Mike software to some more recent developments where we're using Blender and VR goggles to look at inundation, or QGIS plugins that we have as well to facilitate the visualization of model results. And then, of course, we'll leave some time for questions and answers. So first, starting off here, we're going to introduce this concept, of course, of compound flooding in coastal communities, which, again, I'm sure most of you are familiar with this. Really, compound flooding, this is a pretty nice graphic of the effects that we're looking at. And essentially, we're looking at coastal drivers such as storm surge and waves coinciding in tidal environments, of course, with higher tides. And of course, in lake environments, water levels also vary depending on seasonal effects that can vary the lake levels, which we'll get into as well. And this is combined then with drivers from the land side, which are either pluvial or fluvial flood drivers, so rainfall and riverine overbank flow that can combine and compound the zone where flooding occurs. And this also makes flooding a lot more complex process and in some cases more unpredictable. So compound flooding occurs when multiple flood drivers coincide, often leading to higher water levels and more extensive flooding than would be caused by individual driver alone. And here are just some examples, like I've mentioned before: tidal effects, storm surges, riverine flooding, everything from rainfall-induced pluvial flooding to, of course, also future slower processes like sea level rise and land subsidence, which then can, in the long term, exacerbate flooding when combined with these other drivers. There's also changes, of course, to weather patterns and potential changes seasonally on the Great Lakes, for example. There can be changes to ice cover, which could have a big impact on the development of waves and strong wave climate, which can coincide with potentially higher water levels, therefore causing greater flood risk. So there's a lot of things to consider. And some of these are slower timescales and some of them are longer timescales. And it's about trying to understand when these things intersect and the likelihood of those processes intersecting and combining to create flood hazards. So as the climate warms, many models predict more frequent occurrences of increasingly wet storms in the coming decades. And this is really something that we saw, for example, in 2017 during Hurricane Harvey, where we had a combination of somewhat moderate but long-lasting storm surge with extreme precipitation. And this compound flooding resulted in very large inundation areas across the city, which really caused, of course, tremendous economic and also social hardship to the city of Houston. So the concept here is that, in the future, as we have things such as rising sea levels and or changing behaviors of storms, this is certainly going to become a topic that increases in relevance and importance for planners and at the various agencies dealing with flood risk and flood hazards. So why urban coastal compound flooding matters? Well, I mean, the reasons are relatively obvious, but of course it poses a tremendous threat to lives and property, and it can cause more rapid onset intensification of flooding, which is often also more unpredictable when it's coming from various sources. There's compounding economic impacts. We have potentially limited drainage capacity to deal with several sources of flooding, and we'll show you in our case study a situation where there was a lot of sewer backups happening because of the storm surge that is occurring across the waterfront of Buffalo. So quite a few of interesting impacts there. It does amplify infrastructure vulnerability. There are, of course, always environmental consequences as well with these events: erosion and habitat loss, contamination of waterways, etc. So certainly there are many reasons as to why these mechanisms of coastal compound flooding matter. So how does one proactively address the potential for coastal urban compound flooding? And I think a lot of agencies and organizations are very busy investigating this precise question, and there are many tools available. There are, of course, scientific tools, engineering and analytical tools, and policy instruments available to deal with the threat of compound flooding. These things culminate in relatively difficult decisions as to where to make investments and how to strengthen infrastructure and the resilience of infrastructure from multiple threats. And one of the key components that forms the foundation of this is a risk assessment and mapping process. And really, a lot of mapping and risk assessments these days really need to incorporate and consider pluvial, fluvial, and coastal flooding together, especially in coastal cities and vulnerable coastal cities. We often consider these in areas along, for example, the US East Coast, but what we'll show today is that this is particularly relevant as well to large cities along the Great Lakes, which also have considerable risk from compound flooding. The integration of climate data is, of course, very important, and as our understanding of the future climate evolves and also becomes less uncertain, we must incorporate these things as well. Then from there are various other things. Community engagement and education is a large component as well. Having the public understand some of these hazards and risks and communicating those to promote flood resilient behavior is a cornerstone of part of this work. Typically, because of the nature of compounding floods, it's also requiring quite a lot of partnerships. You're dealing with utilities, you're dealing with perhaps transportation and or other sort of public works types of groups that all have to work together. And that makes it quite a multidisciplinary and partnership related issue that has to be addressed. So there are many things that can be done to proactively address potential coastal urban compound flooding, and we'll get into some of these today, specifically the ones here highlighted in orange. Ultimately, this has to lead to improving our adaptation to these types of events, whether through infrastructure, through policy, or through emergency management and other areas where improvements will have to be made. So going back to the mapping component, which is one of these cornerstones upon which decisions can be made and planning can be done, when we're thinking about compound flooding, this really does require an integrated modeling technology to capture these multiple and varying flooding mechanisms in complex urban landscapes and environments. And that's really going to be the focus today, is how to address that. So to do so, in this particular case, we've used our mic powered by DHI application because we are coming to you from DHI, and we have developed an extensive suite of numerical models over the decades now, which are by nature integrated. And that is very much a benefit when assessing compound flood risks, is this integrated modeling technology. Today, specifically, we'll be looking at the integration of MIC 21.3 and MIC Plus, which is really the urban environments with the coastal environments. And what we want to demonstrate is that it's foundational to compound flooding to model all the interactions between mountain streams, for example, sea, lakes, drinking waters, and also subsurface waters. So naturally, the mic powered by DHI products are well suited to assessing compound flood risks. We also do have a special software offer for those attending the webinar today. As a registrant, you may be eligible for a 20% discount. There is a code, Coastal20, which can be used. This is available up to the 31st of December for new registrants. So please don't hesitate to reach out after this webinar to learn more about this special offer that we have for you today. So without further ado, we're going to jump straight into our case study. I think case studies are the best way to learn and to demonstrate application of tools and methods. I think you'll find that some of this may be extremely familiar and perhaps are already methods and practices that you've had in place and used yourself for a long time, whereas maybe other things that we'll show you today are new and perhaps interesting to you. So please do bear with us if there is things that we show you that perhaps you're already familiar with. And we do hope that all of you get something out of this particular case study. So before we jump into this, I would love to acknowledge our project partners who are foundational and important to this project. We worked for the Buffalo Niagara Waterkeeper together with Ramble for a project that was funded through the Ralph C. Wilson Foundation and supported by the City of Buffalo. And this project was approximately 1 year, a little bit less for the modeling. And the context of it is essentially there is a lot of flood hazards currently occurring along the shoreline of Buffalo. The 100-year Lake Erie water level was met twice in the last 15 years. There's heavy commercial and residential development along the waterfront, which is vulnerable and has been prone to flooding, and specifically during seaching or lake surge events. And we'll get into that in a little bit more detail, of course. But this flooding is driven predominantly from storm surge from Lake Erie. There's also many vulnerable communities along the waterfront, and a lot of the infrastructure along the waterfront is either aging or in need of retrofit and upgrade to meet new climate-driven stresses and demands. So one of the very interesting phenomena on Lake Erie that some of those on the call are likely very familiar with, whereas others may not have seen this, is this concept of pretty significant setup that can occur on the lake. The orientation of the lake and its shallow nature makes it prone to seiche, and the difference can be pretty profound. So you have Toledo towards the west of the lake and Buffalo towards the northeast of the lake. And during large storm events, specifically when winds are driving towards the northeast, you can get significant water level differences, up to 17 feet across the lake between these cities. And this drives a lot of the water towards the northeast, and it piles up on that side of the lake, creating a significant storm surge and thus a significant flood risk. So The other thing that happens after these events occur, there's some sloshes that happen after this peak event, and this really is a major trigger for flooding. This can be combined with significant rainfall events that further increase the amount of discharge from rivers and local ponding and pooling of water that then compound with the surge to essentially amplify the flood impacts. Additionally, we have during these storms very strong wave growth across the lake, and we have wave run-up overtopping of relatively low breakwaters and also revetments and seawalls causing damages and erosion locally along the shoreline, and in some cases, extreme cases, ponding and pooling of water as well. So there is certainly a whole combination of mechanisms that cause flooding, which then, of course, we now refer to as compound flooding. So there's also changes to the climate, which increases complexity here. For example, last year, we've had some of the lowest ice coverage on Lake Erie historically, and the ice coverage is quite important, not only in the winter, but in the shoulder season specifically when it's quite stormy. And it prevents the direct impact of waves and or wave growth across the lake during large storm events. And so without the ice, there is more potential for large wave driven flooding to occur along the shoreline. We've also had periods of prolonged high lake water levels in the last couple of years between, say, 2015 through 2019. So with these changes in static lake level, and if the lake levels are higher due to a lot of precipitation and moisture in the Great Lakes Basin, these surge events become much more impactful than if the static lake level is lower when there is less water in the lake itself. So these are processes that need to be considered, as well as into the future, and of course also looking at past events. And what we saw was, of course, in the last couple of years with these high static lake levels, there was significant flooding along the shoreline of Buffalo. So more frequent impacts required that decision makers and stakeholders need to develop, again, this comprehensive understanding of vulnerable assets through mapping, initiate dialogue amongst community members to seek solutions and to also understand where the critical areas are that impact communities, developing these proactive measures to reduce flood risk. And in this particular case, we're looking at developing several projects throughout the area, including natural nature-based solutions to address some of this flooding. And finally, of course, we need to look ahead at how climate change will further exacerbate these issues and what can be done with adaptive management planning and policy. So the roadmap, and this is specifically DHI's component of this project. There was other components done by Ramble, but we very much focused on the modeling, was to first look at the situation regionally. So we'd have a regional model of Lake Erie, across which we simulated these various storm surge and seashing events. We then had a citywide model, again, where we're driving the model with things such as river discharge and looking more at additional overbank flooding that will occur concurrently with the storm surge. And then we had sort of a lot level local assessment where we're looking at inundation, and we also did an analysis of extensive wave run-up and overtopping along the shoreline that coincided with river discharge, overbank flooding, and storm surge. We also will address some of the sewer backup issues that we had analyzed as well with Mike Plus. So the first step is really developing your model scenarios. And this is going to be just a quick overview of what data we looked at. Again, most of you will be familiar with this process. So it's just a matter of going through some of these steps of developing the model scenarios before the modeling actually takes place. So in Buffalo in 1988, they established several return periods for extreme water levels. And this was derived using a log Pearson type 3 approach. And to this day, this is definitely still referenced relative to international Great Lakes datum with the various return periods. One of the first things we did was revisit this analysis from 1988 and update it with more recent data. So there are, of course, water level monitoring stations throughout Lake Erie that can be used to calibrate the regional model, but can also be used to understand the seashing effect. And in fact, the U.S. Army Corps recently did a very interesting study that was discussed and I think published this year, looking at all the water level gauges around Lake Erie and doing an analysis on those, which is very comprehensive. So I certainly recommend you look for that study and look at some of the analysis there. So we first started focusing a little bit on the water level station that exists on the waterfront in Buffalo, and there's various data sets, and we're very interested in this verified hourly water level data, which is available from 1960 to present day. There's, of course, also verified mean daily water levels available from before 1890, so a very long record, which is good to understand sort of more long-term trends. But when it comes to storm surge, we're very interested in things such as winds and sub-hourly or hourly water level observations, really a higher fidelity data. So the 1988 report, the analysis was based on data from 1918 to 1987, whereas we were looking only at the hourly data from a period of 1960 to 2024. And what you can see here is, of course, that annual variability in water levels, but on top of that annual variability, you have the fluctuations due to atmospheric conditions. And this is just a quick assessment that pulls those pieces apart. So you're looking at that time series, and then you are able to discern the still water level, which is the water level at which the lake fluctuates, much more slowly, seasonally, or over the course of a couple of weeks. And then the surge, which is really the atmospheric component that fluctuates much more rapidly. And it's, quite easy to pull these apart. And then you get a good understanding of the surge events that occurred at this particular gauge. Then, we did a series of different joint probability analysis looking at the relationships between total water level and surge. And of course, it's not necessarily a surprise here that, you've higher total water levels that are combined with high surge events. And we can even, in this particular analysis, pull out specific storm events of note that, were known to have caused significant flooding. So the residual water level, again, is that surge, and then the total water level is that combined surge and still lake level, and then we have that for certain return period events. So that forms some of the basis of understanding really sort of the magnitude of events that we need to look at. We also need to consider climate change, and there's been some really great work done in the last 2 or 3 years on future lake levels, and this takes into account the entire basin hydrology of the Great Lakes. There is more recently a consensus that there is a potential for the Great Lakes Basin to become slightly wetter into the future, and therefore there to be more moisture in the basin, which could potentially slightly increase lake levels. This is a conservative assumption in terms of the modeling. These assumptions, were taken that we are going to have slightly higher lake levels in the future. Again, this science is constantly changing and evolving, and there has been consensus in the past that lake levels could be lower, and now there are potentially research pointing to lake levels being higher into the future. So we referenced the work from Siglinix and Temgoa in 2022 to establish some higher lake levels for future scenarios to look at. And again, that is a bit conservative instead of some of the other research that perhaps points at other trends. The discharge of the Buffalo River. So we had several rivers discharging into our domain, depending on whether or not they were part of the study area. Skajakwata Creek and Buffalo River were incorporated. For the Buffalo River, there's sort of 3 main gauging stations that were incorporated, and then there's of course also the watersheds downstream of those stations that were incorporated as well with some rating curves. We combined those discharge data, and we then also accounted for the area downstream, and we derived annual and also seasonal return period discharges for those rivers. We also looked at the seasonal component because that's when we had a lot of the particular flooding events occurring, and that season where there's prone to the surge and the seashing. We also compared them to literature from other studies where people had done a more in-depth assessment of the watersheds and discharges of these rivers to make sure that our numbers and our assumptions aligned with literature. You can clearly see in this example, December 2021, that there's a corresponding amplification of water levels in the rivers associated with that surge. So really that surge is driving up the rivers during these events and causing overbank flooding and flow. And we also saw there was discharge that significantly increased as well during these events. Some correlations that could be looked at in terms of discharge versus the residual, the surge residual, trying to understand what kind of river discharges occur during these types of storm events and what kind of magnitudes of river discharge should we incorporate. We in this particular study, we only had, say, the resources to do a few event-based simulations. It would be, of course, preferable to do ensembles of simulations or more rigorous testing to look at a variety of scenarios, but we had to be somewhat discreet in what we picked as our scenarios, and thus we were forced to really use this observational data to select a few interesting scenarios and also historical storms to simulate. So then finally, we generated our table of simulations and scenarios, and this is essentially, we had, again, a budget to do about 10 scenarios. And really what we did is we had 3 calibration events that we simulated, which aren't in this table, and then 10 scenarios where we're varying essentially the return period based on joint probability analysis of surge and total water levels. And we're combining that with different discharges from the rivers, and also 4 scenarios with some climate change increases in total or in the lake level. We didn't really play with ice as a major factor. We assumed there was no ice. Again, that is the most conservative assumption. So finally, I'm going to, I guess, turn it over now to Renan to talk a little bit about preparing all the input data for the actual modeling itself, which was done in the Mike 21 FM hydrodynamic model. So Renan, take it away.
Thanks, Duncan. So I just would like to share with you some typical model input data that we use, and I'm pretty sure that most of you are familiar with these data sets. But I also would like to highlight some Mike tools that we can kind of easy get this data and build mesh and force the model. So first of all, we split the typical model input data into that type of data sets. The first data sets to build the model mesh. So of course that we will need the coastline shape files represent the coastline, the shoreline of the lake area, for example. We will need in this type of modeling the building footprints. We will also need detailed bathymetry, detailed topography, mainly came from LiDAR data sets. In terms of environmental forcing, we will need, of course, in this case of study, the atmospheric conditions, especially the wind and atmospheric pressure that drives mainly these SAISH events, for example, in Lake Erie. We also, of course, need river discharge, water level, not only to force the model, but also to calibrate and validate our model, and waves, for example. And just to have a quick overview of one of these data sources, we can, for example, get the buildings from OpenStreetMap. We can take from Google Research Laboratory. We can also take the building footprints from Microsoft database. We will share this presentation with you so we can just check after these links and this database. In terms of bathymetry, just some examples in a global scale and national scale. We have the JEPCO database that it's kind of CURS database from the global ocean and lakes area. And we also have, of course, the NOAA database that there are a lot of information, single beam, multi beam, and also bathymetry and topography, LiDAR data sets along Lake Erie. For example, we have also information from Government of Canada. So just a quick overview of the main common database that we use. But yeah, we can simply get all of this data with a single tool that we have here in the HI. That's the Mike Mesh Builder. That is a YouTube video, and we can check after the the meeting. But just to highlight some features that we can do with the Mike Mesh Builder, we have for example, the OpenStreetMap database inside the Mesh Builder. We can just draw a simple polygon in our area of interest and get for example, the coastline, the roads, the buildings, the riverbed. We can also get bathymetry data. We can also have a different source of information. For example, we can get the coastline from NOAA database instead of getting the coastline for OpenStreetMap. Just clicking, just by 1 or 2 clicks, we can get all of this information. For example, on the next slide, we can see the building footprints from Microsoft, and we can get the building footprints. This is the raw data, and we can, after getting the raw data, we can, in the tool, we can simplify the polygons, we can dissolve the polygons, we can clean small polygons, and just to have the information that we need to build our mesh in a good way. So here's an example. We can just take the buildings, the roads, we can draw we can take the coastline, we can draw the polygon of our area of interest, and build just with some clicks our mesh in our area of interest. And in terms, and of course that we can also interpolate our bathymetry. We can get more detail and input a more detailed bathymetry and topography on the tool and interpolate it directly on the cloud. So just to highlight some of environmental forces that probably you are already familiar with. The main drive for this type of modeling is the atmospheric forcing. We have different sources such as CFSR, ERA5. In terms of forecast, we can get data from GFS model, ICON model from Germany. In terms of river discharge, we have a strong database from Water Office of Canada, USGS. In terms of global data, we can grab that, for example, for the Global Flood Awareness System from the Copernicus database. And just a few examples of another environmental forcings and data that we will need to build this type of modeling. Just some water level data, wave data along, for example, along the Lake Erie. And of course, if we are working in coastal and marine models, we can use global models for the coastal downscaling, such as global tide models from DTU, TOPEX, and also global models such as the Copernicus model and HICO model. So again, we have a nice tool to grab all of this information and environmental forcings. That's the Mike Data Link. It's a cloud platform that you can, after building your mesh, you can just input the mesh on the system, and you can just easily set up the start date of your model and the end date, and you can grab, for example, the ERA5 atmospheric forcing or the CFSR atmospheric forcing. And if it's, for example, on a coastal and marine model, you can build your own environmental forces, boundary forces from HICON, from DTU, and another data sets that we have available on our platform. And now I just would like to introduce you just a little bit about the setuping this regional model that we did for the project. And of course, that although the Mike software offers a versatility with its use of flexible meshes, these downscale techniques are often essential to reduce mainly the computational costs, while ensuring to accurately simulate the various factors influencing urban flooding. For example, here in Lake Erie, as Duncan mentioned before, we have the SAGE driving mainly by wind, and of course that it will be difficult to simulate this phenomena just considering a local model. So we need to consider a regional model, and it was what we did. So then we can also play with different scenarios, for example, increasing the lake level, increasing the wind speed and the intensity of winds and frequency of these storms, for example. And what we did, we built a mesh for the entire lake area. It has almost 9,000 elements. The resolution varies from kilometers to some meters or feet, 50 feet around the Buffalo area. use the main boundary condition that we use in this model, just grabbed by that database that I mentioned before. It's the Niagara River water level. We use also St. Clair River discharge, the main river discharge of Mamou River that stays around Toledo, and of course the localized river discharge from Buffalo River and Scajaquara Creek. And I just would like to highlight another nice feature that we have on our mic software. It's the hydraulic structures. So we can, in spite of having this regional model, we can considering this type of structures, different type of structures, to be honest, and our model, for example, we can consider in the breakwaters that's showing this figure on the right here as a weir structures. We can consider in the cuverts on the Bird Island Pier. We have a lot of cuverts, and of course that in a regional model it will be difficult to implement in the mesh inside it, the mesh, and we can consider it as a sub-mesh or sub-grid feature, and the mics allows you to play with different type of hydraulic structures, such as bridge pillars, for example, and others. And of course, that the main drive of the SAGE phenomena, it's the atmospheric force and the wind, and in this regional model, we kind of use a good wind model. That's the HRDPS, the high resolution deterministic prediction system from Canada. Use, as you probably are familiar, mainly the wind and pressure gradients of the wind. And it's nice to see on this picture on the right that we have a good representation of wind. We select some storms to simulate, for example, the first storm at the top of the rank of all of these historical data that we have. It was the 2020, and we could represent properly all the SAGE effect. We can represent the still water lake level on all of these storms, and we was happy with our regional model calibration and validation. And after, and just to let you know, here's just a simulation of the model results for one of these storms, December 2022. And in these storms, the model indicates a difference between the Toledo water level and the Buffalo water level on the northwest side, about 10 feet. So the water level reached out almost 580 feet on the Buffalo region. So after doing this regional model, we start building our local model, and just would like to highlight that in my software is super easy to do this kind of downscale process. I know that with other models, we need to kind of pre-process and or post-process the model results to build the boundary conditions for the local model, but it's in Mike, it's super easy. We can just take the output, our DFS1 files, for example, and use as input on our, use as an input of our local model. And so to do this local model, it was more or less the same procedure, of course, having the building detail information regarding the coastline, the mesh, the buildings itself. So for this local model, you use the very detailed bathymetry, not only bathymetry, but also topography from a good LiDAR product that we have from New York State. It's very detailed, and also it's important to consider this very detailed input data for this kind of local lot level model. We also considering the buildings itself. We use the Microsoft building footprints database. We adjust these buildings based on recent satellite images, because most part of the time these data sets could not be up to date. And of course that we needed to also adjust these buildings to properly represent the mesh. For example, on the next slide, we have some information that we get from the database, the roads in green and the buildings aggregate represented in red, and some parts of the buildings, for example, they are not. We need to attach it for the roads to avoid small elements and sharp angles when we start building the mesh. We also did sensitivity analysis on model mesh, trying different approaches to represent these buildings. One of them is called building whole. And to be honest, we didn't represent the building itself. We just do it as a whole on our mesh. And also the other approach is the building block approach. And we test this different approach, the different mesh resolutions, and to check the best way to simulate this flooding. Also consider, of course, the computational costs to simulate this phenomena in urban areas. So at the end, we build a super high resolution mesh around 1 million elements. And another nice feature that we have in Mike is the possibility to parallelize the model, the simulation, not only using the CPU, the cores. Today we have a lot of cores in the computers, but we can also parallelize the model using the GPU. So for this model, for example, we use the Mike 21 model and parallelize on GPU. And here is some images showing the high resolution mesh that we have around the city, about 4 meters of resolution, 10 feet of horizontal resolution, and highlighting a region, this first ward neighborhood here that's has a low topography area and potentially could flood in strong events. And it's a super high and detailed mesh. And we also calibrate and validate the model with data from that source, just to ensure that the local model are also propagating the SAGE from the boundary. And it's also important to validate our model results with floating data. And of course, it's difficult. We don't have gauges in all of the corners to check if the model results are representing, measuring data, but we have good information regarding the experience of people, and we engage some stakeholders on this project. For example, the city of Buffalo. We have some information from the city, from the Dom Poleto, some nice pictures and showing the damage caused, for example, from this November 2020 storm and the December 2021 storm as well. We can see the flooding below this highway here on Skajacada Creek, and model could represent properly this flooding in this area, and we was happy with these results as well. Another type of information that we could use to try to do this validation, the qualitative validation of the model results, is some information from Twitter, for example. We have Twitter, or X now, sorry, and we have this information from the Buffalo Police Department reporting some flooding around the First Ward neighborhood, and our model results also show this flooding during one of these storms that happened in the past years. And after doing all this calibration and validation process with these storms, we started simulating the different type of storm surge event, 100 year, 500 year, considering climate change. And one of the things that we also considered in our simulations is some future scenarios considering planet structures. For example, this new structure that in fact are happening, the construction of the Sentinel Park, and we could implement this new structure in our mesh and check before the construction, of course, the benefits in terms of preventing from flooding of this new structure. So that's it that I would like to share with you today, and I will hand over to you, Duncan.
Thanks so much, Renan. And yeah, folks, I do apologize. We are running a little bit behind here, but we'll try and power through to the end. So if I do go a little faster, I do apologize for that. So the other thing, of course, is waves, and waves play a significant role in damages along the shoreline of Buffalo, and they create overtopping and run-up that creates ponding and pooling in certain areas, and we wanted to understand that process. So the methodology here was very similar to the one that Renan showed, which was a downscaling of a regional lake-wide model. We essentially, because we didn't have much time, used the WIS model, which we downscaled to a local Mike 21 spectral wave model, and then we built a Mike 3 wave FM model to look at the more complex dynamics along the shoreline, and that includes things like overtopping, inundation, wetting and drying, etc. So the mesh for the Mike 3 wave FM model was very much based on the existing bathymetry and topography that we'd interpolated for the previous models, except for, again, a higher resolution. There's a lot of complex structures and low crested breakwaters, concrete breakwaters, seawalls, all kinds of different permeability and reflection coefficients for these. So they had to be integrated, quite precisely, all these different types of structures. The model is based on non-hydrostatic 3D Navier-Stokes equations. It's definitely computationally a little bit heavier of a model, but it's significantly faster than, for example, a CFD model. So these are just some simulations of the domain, and we see, very much the dynamic nature of these waves and the impact on some of these particular areas, such as the park in the northeast or northwest of the domain, where we're seeing ponding and pooling and quite a lot of impacts from wave effects along the shoreline during this surge event as well. So it's coinciding. And I wanted to show just a quick aside is, the Mike 3 wave FM model, it had some impact in Buffalo, but there are other areas where it has a much more profound impact. So this is on the east coast of Canada and Newfoundland. When Hurricane Fiona passed, a large portion of the damages that were done in coastal communities there were associated with compounding surge, but also wave setup and wave effects. And I think this simulation that we've just recently completed here in Port aux Basques, which is one of the communities that was affected, really shows the power of using a model like Mike 3 wave FM to look at the flood impacts that waves from a tropical cyclone can have on a community. For example, here you see a large rock island and formation that is relatively elevated during calmer conditions like you see here, and the perception from the community is that building your homes close to the shoreline behind this rock island is relatively safe because it offers protection. It's almost like a natural breakwater structure. This is a picture that shows some of the damages of homes that were impacted in and behind these large rock islands. And you see then with a program like Mike 3 wave FM, you're able to capture that process where a combination of surge and wave setup actually creates significant overtopping and wave effects that come across this, what appears to be a very large natural feature, and therefore impacts a lot of the communities and homes along the coast. So this is just an aside to demonstrate sort of the power of this tool to look at more complex flood mechanisms from waves. In Buffalo, another issue was the backup of sewage during these surge events. This is a photo from a basement in Buffalo in one of the areas where there was sewage backup. So what we essentially did is we took the model and we integrated the boundaries from our Mike 21 hydrodynamic model to Mike Plus, and we incorporated the swim model that the city of Buffalo had into Mike Plus as well. And what we did is in Mike Plus, try to understand what are the contributing drivers to sewage backups in people's homes. And really what it shows was that flooding was primarily due to storm surge and not necessarily backflow from outfalls, not necessarily inflow from precipitation, which is an important finding. So I'm not a urban or engineer myself, but this is certainly another powerful extension of the Mike suite of software to integrate some of this analysis of storm surge through the sewer network in Buffalo. And then ultimately what we did is we looked at the structures that were impacted by this, and I tagged and identified those structures and identified the freeboard within those for the hazard and risk assessment and mapping assessment. Finally, there's many other applications that you could extend your model to, whether it's water quality investigations, flood mitigation solutions, environmental impact assessments, etc. But that's not the focus of today. I think we're going to wrap it up now with some really interesting ways to communicate your model results, which I'll hand over to Derek.
Yeah, thanks, Danker. So this final part of the webinar is focused on visualization of Mike model results and taking your models and turning them into compelling and informative visuals that can help with communicating results and the different ways to do that exist in the Mike software suite. So very quickly, why is this important? I think these are things that we all inherently know about why creating compelling and informative visuals of modeling results is important. But just to list a few out, it can lead to a better understanding of what's going on and more valuable and richer engagement and interaction with clients, stakeholders, and the public, and provide a means of more effective communication by breaking down the barrier of having to understand scientific plots and numerical modeling results and things that may or may not be immediately obvious to people in other fields. It can help with identifying patterns and trends in the model data and identifying errors, and in turn facilitate more informed decision making, and of course can bolster confidence in the underlying modeling. So we wanted to provide a quick recap of visualization techniques available in the Mike software suite before getting into some of the more innovative and recent developments that are going on here at DHI. Starting with Mike Zero and the Mike Zero toolbox. Mike Zero is the default data visualization software that comes with any Mike subscription. This is the program that gets launched when you double-click a DFS file, and while it's a bit more on the simple side, you can create some really good-looking stuff in Mike Zero by visualizing DFS file data and overlaying shape files and aerial images and things of that nature. It's really kind of the go-to that you would use to produce presentation quality plots and animations quickly when you need them. And then there's the Mike Zero toolbox, which also comes with any Mike subscription. This is a set of tools that can be used to convert Mike model results into different formats, such as DFS2 and DFSU files into shape files, which you could then use in another software like a GIS environment to leverage the host of functionality available there. And along that same train of thought, there's also the Mike QGIS plugin for the QGIS software, which is a free GIS software that I would say is pretty commonly used in the industry and in academia. So at DHI, we've developed a plugin for this software, which allows you to interface with DFS files of Mike model results, where you can simply just drag and drop your DFS files onto your QGIS screen, and it will open and visualize them and provide you some options in terms of what data to show and how to show it. And from there, you can leverage the host of functionality available in QGIS. There's a very large toolbox of functionality you can use to analyze your data and develop statistics and make contours and convert to different file formats, and really a whole rabbit hole of useful and interesting operations you can perform on your data once you get it into QGIS. And you can also make presentation and report quality visuals and maps that include aerial imagery and other supporting vector and raster data sets. And the Mike plugin makes this all very easy and is very simple to use. This is available to download for free on the DHI website, and there are tutorials of how to use it available on the DHI YouTube page. I also wanted to quickly mention Mike.io, which is a very popular Python library that's available for free on the DHI GitHub and provides an API to perform input, analyses, and output operations on all the different Mike file formats. This allows you to take advantage of the numerous analysis and plotting libraries that exist in Python, such as Matplotlib and Plotly and Bokeh and other popular ones. But it also has some built-in plotting functionality to make very nice looking visuals of Mike model results with only a couple lines of code. This is a very popular Python library that's under active development and is always continuously improving. And as I said, it's available for free to download and use from the DHI GitHub. And this includes extensive documentation as well as example scripts and Jupyter notebooks to help you get started and explore its capabilities. And for anybody who's interested further, there's also training courses offered to the public by DHI, and there's actually one starting next week. So if you were interested in that and wanted to get registered, just check out the DHI Academy website and search for Mike.io. And now we'd like to introduce Mike 3D Studio. This is an add-on for the software called Blender, which is used for creating high-quality 2D and 3D visualizations and animations. The add-on installs some DHI functionality into the software to allow you to import and interface with model data inside of Blender. This includes all the typical DFS and Mike file formats, and also another of other common file formats like GIS, vector, and raster files, VTK, STL, OBJ, NetCDF, and grid files, and other common model output formats. It also has functionality to easily integrate aerial imagery and terrain data, 3D buildings and 3D models and other real-world assets, in some cases connecting to online databases such as OpenStreetMaps and the SRTM terrain database to easily fetch this data with only a few clicks. Blender is a fully fledged production suite for high quality visuals, and you can see some cool examples on this slide. This is a new and active development going on here at DHI and something that we're using internally on projects and trying to gauge market interest to develop a path forward to commercialization. So if this is something that interests you or is of interest to your company, we'd very much be happy to hear it, and we can integrate that interest and feedback into our plan going forward. And over the next few slides here, we just wanted to show off some of the Blender capabilities in relation to the Buffalo flood study. So as Renan described, we started off with a lake-wide model of Lake Erie to model the large-scale surge on the lake and develop boundary conditions for our local model at Buffalo. This is just a shot of the underlying bathymetry that we used, as well as the mesh in the order of 100,000 elements across the entire lake, getting down to about 50 feet in size around the shoreline and at Buffalo. And we've visualized the mesh in Blender here with an aerial image underneath just to make things a bit more tangible. This is what the mesh looked like once the model domain was fully discretized and had the underlying bathymetry interpolated onto the mesh. And as Renan mentioned, we drove this model using regional scale atmospheric forcing for select events to understand the surge profile across the lake and develop boundary conditions for our local model at Buffalo. This quick animation just shows that effect for the extreme notable event that occurred at Buffalo in December of 2021, or 2022 rather, and highlights where Buffalo sits in the grand scheme of things. And yeah, so zooming in a bit to downtown Buffalo, this is a 3D model we built of the city using open data sets in the Blender software using Mike 3D Studio, using a combination of aerial imagery and bathymetry and topography data sets, LiDAR data sets, 3D buildings, and kind of whatever else we could find to help make a compelling and realistic looking scene. And this slide here shows the detailed mesh that was created for the local Mike 21 FM model, getting down to street level resolution and snapping around individual buildings and structures in the order of a million elements, getting down to 10 feet in size at the highest resolution areas. This is the roughness map here that we used for the modeling, black being the lowest roughness and white and red being the highest roughness areas. And you can just visually see the level of detail that went into this model and being able to capture the different pathways for floodwaters along the roads and in overland areas. A lot of hard work and effort was put into developing this model domain to capture local effects as accurately as possible. For this study and this extreme event, there were a handful of specific areas along the waterfront that were particularly impacted, one of them being shown here on the left with a kind of blue lake watercolor and on the right with colored depth mapping contours, showing the impact of the storm over the duration of the storm at this location and what's possible in the Mike 3D Studio add-on in Blender. And yeah, with all the underlying data sets, we were able to capture the local flooding areas quite accurately and provide something very digestible and relatable to the client, stakeholders, and the public. For this study, we also leveraged the Mike 3D Studio add-on capabilities to develop virtual reality content for our client and for a public engagement session where we essentially rendered a 3D model of the model and flooding in the city into a virtual reality compatible format and loaded it into a Meta Quest 2 virtual reality headset. This shows what our engagement session looked like and some examples of people viewing the data in the headsets. And the little video on the bottom left of this slide shows one vantage point that people were able to place themselves at and pan around and look at the flooding that we simulated and compare it to what they experienced in reality during that storm. So this capability of the Mike 3D Studio add-on is very valuable. That can generate immersive content that pretty much anybody can relate to and understand. So last slide here on visualization of Mike models. Like I mentioned at the beginning of this section, having these types of engaging and informative visuals makes the modeling results more digestible and accessible to clients, stakeholders, and the public who may or may not be as well versed in numerical modeling and can facilitate more meaningful and efficient communication and storytelling, and ultimately decision making based on what they're seeing, and of course bolster confidence in the underlying modeling. We recapped a few existing options for model visualization in the Mike software suite and leveraging of other software that Mike has plugins or integration for, and also showcased some of the capabilities of the Mike 3D Studio add-on for Blender, which is geared towards the high quality production level visuals and animations. As I mentioned, this is currently under development and we're sorting through a path towards commercialization. So if anybody here is interested and would like to learn more, we'd really appreciate if you reached out and shared that interest with us. And I'll pass it back to you, Danker.
Thank you very much, Derek. Yeah, so we're just going to wrap up here now. So I hope you found this webinar interesting, and we'll certainly circulate the recording and the slides. We're also, of course, available for any questions you may have. You can email us, reach out to the Mic Academy team or the Mic software team. Again, I just wanted to reiterate that we do have a special software offer available, so please do look out for that, specifically to those attending this webinar. And finally, we have another series of this coming up in November. 13th of November, we have another session here, how to assess coastal erosion and shore protection schemes as part of a shoreline management with Mic powered by DHI Tools. So we look forward to welcoming you again to another session on the 13th of November. But that is it for today.